Okay, this problem involves a little bit of disgusting algebra. I hope I will get it right on the first try. Um, the thing that is different about this problem is that the collision is elastic. So that means that both kinetic energy and momentum are conserved. Now, if we use the hint given in this problem, um, and we look at this triangle, so I'm going to zoom in on this a little bit further. So that triangle is part of a larger equilateral triangle. Since this triangle here is equilateral, let's use the line tool to get it drawn straight. I am bad at tablets. That means that this angle is 60 degrees. This whole angle is 60 degrees, which means that theta drawn here is 30 degrees. We will need that later. Actually, I'm just gonna draw my arrow over somewhere else and say theta is 30 degrees. I'm going to annotate this with a cartoon of what happens after the collision. So after the collision, this top ball goes that way, bottom ball goes that way, and the cue ball, I do not know its velocity. I don't even know if it's to the left or to the right yet, but I'm going to label those things. So we'll call this V1, that V2, and the motion of the cue ball Vc. And again, I know that that angle there is 30 degrees. So I know that momentum and kinetic energy are conserved. So the conservation of kinetic energy equation tells me that 1/2 mvc squared, well, v naught squared, so that's the kinetic energy in the beginning. So I'll refer to that as v naught, equals the kinetic energy that the cue ball takes away at the end, plus the kinetic energies of the two other balls that have been struck. mv1 squared plus 1/2 mv2 squared. Can cancel the m's, can cancel all the 1/2s. And so we probably can see right away that v1 equals v2, right? We can argue v1 equals v2 by symmetry. I'm not going to do that yet because we can see that come out of the conservation of momentum. Yeah, we're going to get there. But we'll get there a little bit later. So the conservation of kinetic energy equation then becomes v naught squared equals vc squared plus v1 squared plus v2 squared. We also have the conservation of momentum in both x and y. In x, that tells us that mv naught equals mvc. Again, I don't know whether that'll be positive or negative. plus mv1 cosine theta plus mv2 cosine theta. In y, we have, so there's no initial momentum in the beginning in the y direction, equals mv1 sine theta minus mv2. Whoops. mv2 sine theta. So this tells us right away that v1 equals v2. And so I don't have to keep writing those. I'm just going to label that as v. So I'm going to use the symbol v to mean the velocity of either ball after the collision, not the cue ball. So here in the problem statement, I'm treating this as v naught. Rearranging the notation a little bit just to make my life easier. In the conservation of momentum in the x, of course, I can cancel all the masses. Whoops, I should have written, it was my mistake there. That should be mv2 cosine theta. But we recognize that v1 and v2 are both the same. So now we've got some algebra to do. Our system of equations becomes, for energy, notice that v1 and v2 are the same, so this gives us v naught squared equals vc squared plus 2v squared. And for momentum, v naught equals vc plus 2v cosine theta. So anytime you have an elastic collision, you're going to have algebra that's a little bit painful. Because here I've got two equations, one of which has a square and one of which doesn't. So the approach that I'm going to take is I'm going to solve the energy equation for the velocity of the cue ball and substitute into the momentum equation. So doing that, so let's just do a little arrow down here. This gets me that the velocity of the cue ball is the square root of v naught squared minus 2v squared. So then when I substitute that into the momentum equation, that gives me v naught equals the square root of v naught squared minus 2v squared plus 2v cosine theta. So this is an equation that in principle I could just solve for v. But to do that, I have to get rid of that pesky square root. I'm going to split this video into two parts now. So I'm going to end the video. I'm going to start recording again in a moment. So click to the second video if you're interested in seeing the rest of the algebra.